Yeah, thank you. Alright, so good afternoon everyone. Welcome back. So the goal is to finish the proof of Brooks Theorem, right? But let's do a quick recap to just see how we reached this point. Right? So hopefully everybody remembers the statement, it's here anyways. Right? So for this we just observed that you consider an arbitrary ordering of the vertices. You have a palette with delta plus 1 colors. Just start coloring. Every time you reach a vertex, Vi, look at the colored neighbors. They use at most delta colors. Therefore, one color is available in your palette. Use that color for this vertex. Observe that this works every time, so you are done. Yeah, so you never need more than delta plus 1 colors because you are done, right? Okay. So therefore, the upper bound of delta plus 1 is proved. And then we made a very interesting observation, which is that for any connected graph, we observed that not only can you color using delta plus 1 colors, you can actually color so that one of the colors is used at most once. So if your delta plus 1 is 5, then out of the 5 colors, one of the 5 colors is used at most once, only for one vertex, possibly 0. Maybe you are using only 4 colors, then anyways it is true. Yeah. And the way we did that is here connected is very important, because observe that if you take two vertex disjoint odd cycles, this statement is false. Take two triangles, why not? Observe that every coloring uses each color at least twice. Yeah. So connected is important, and the fact we use about connected graphs is that they have a spanning tree. So we took a spanning tree of the graph, and what we did is we constructed an order such that for each vertex Vi, I less than n, there is a neighbor of Vi that appears later. Yeah. If we can do that, then it means that when I reach Vi, if I have a palette with delta colors special and one color separated, delta's colors and one special color, okay. If I reach, I will only use the first delta colors whenever possible. Whenever I reach a vertex Vi, because one of the neighbors has not yet appeared, at most delta minus 1 neighbors have appeared by definition of delta, and therefore at most delta minus 1 colors have been used. Therefore I can choose a color from the first delta. At the last vertex, I may be forced to use the delta plus first color. Yeah. So we took a spanning tree and we just deleted leaves one by one in any fashion, doesn't really matter. Just delete a leaf from the spanning tree. Then from the resulting spanning tree of the resulting graph, T minus V of J minus V, again delete another leaf. Keep doing this. At the end you will have a single vertex. Put that as your Vn. Yeah. And observe that this ordering has a property we want. Because whenever I delete a leaf, its unique neighbor is still not in the ordering. It will appear later. Right? Because the neighbor of the leaf cannot become a leaf before this fellow becomes a leaf. I mean, in K2 it's interesting. Both of them are leaves. But anyways, right? Yeah, the neighbor of a leaf is never a leaf unless the graph is K2. Is that correct? Yeah, I never made this trivial observation before. Very trivial. Okay, anyways.
For the first DIY.
Wait. Yeah, let's not jump the gun. So yeah, so for those of you who have figured the DIYs, we are coming to that. I'll come and talk to you all. Right. So now what we are going to do is, so everybody is okay with this. Therefore, there is a vertex coloring using delta plus 1 colors, where at least one color is used at most once. Yeah, funny statement, but true. Yeah. Okay. And connected is important. Okay. So now what we'll do is, we will use some of the same ideas, more or less. Almost the entire proof is about spanning trees. Okay, that's the crux of this proof. We will use some of the same ideas to finish the proof of Brooks theorem for graphs that are not regular, which means there are two vertices whose degrees are different from each other. Yeah. So see if you can finish this, and if you can finish this, just raise your hand, and I'll come and talk to you. Okay. Okay. Right, so only thing you have to prove is that if the graph is not regular, then you never need the last color. Because odd cycles and complete graphs are actually regular, right? So therefore for irregular graphs, delta colors suffice. Okay. And if you have figured that out, the not regular case, now see if you can use the not regular case to finish the not two connected case.
This will just be something else. Intersection of these vertex edges in each of the points an edge. This is basically the same idea, just shorter, faster. Okay. Okay, next. Yeah.
Because it's not irregular, they will color each of them separately, so that with this vertex is the same color.
Anyone else? Yeah. What if yeah, not two connected means there is a vertex you can delete to get a disconnected graph, not necessarily an edge.
If there is such an action, then trying to show like yeah, but if that's that you can have, which is if there are vertices for which there is some which you have to put up in
Okay, so shall we finish off the not regular for everyone? Yeah, everybody's okay with not regular? Yeah? Basically the only problem was the last vertex. Until the last vertex we are anyways not using the delta plus first color. Right? The last vertex will use the delta plus first color only if it has delta neighbors and each of them has used one color and now I've run out of the first delta colors. Right? So that means that in particular the last vertex should have delta neighbors. Right? Well, if the last vertex doesn't have delta neighbors, then I'm just done. Right? So what we can do is if the graph is not regular, choose a vertex of degree less than delta, make that the root of your tree. Root is the guy who is deleted at the end. Every tree except K1 has at least 2 leaves. So at least one of the leaves is not the root because I fixed the root. Yeah? So I will keep deleting leaves that are not the root and at the end I will put the root fellow. Yeah? And that fellow has degree less than delta by choice. So therefore when I reach the last vertex, I still have a color in this palette and I never have to go to the last special color. So we're done. Yeah? Alright, so that's it. So we're done with graphs that are not regular, which is actually interesting because of course odd cycles and complete graphs are regular. So that should be the harder case once you know the statement of the theorem, right? So we are done with not regular, good. Now what we will do is, we will use this fact to settle graphs that are not too connected. Okay, and I want to give you an alternative way of looking at not too connected graphs, which you will hopefully find useful in life elsewhere. a connected graph is not too connected if it can be written as G1 union G2. A connected graph G is not too connected if and only if G may be written as G1 union G2. I'm taking the union of two graphs, which means you take the union of the vertex sets and you take the union of the edge sets, such that their intersection is exactly one vertex. This is the vertex, and each of them has at least one edge, because otherwise every vertex would be a so-called cut vertex. Otherwise this is actually trivial. Each of this is non-empty for I in 1, 2. Let's do a quick example. Of course, here it is clear, if this is my graph, then I just take this to be G1 and this to be G2. Yeah? On the other hand, if my graph is more interesting, let's say something like this. I don't know. Everybody sees G1 and G2. There are multiple choices. Do you see multiple choices of G1 and G2? Yeah. I can take this as G1 and I can take this as G2. Yeah. And this fellow is a cut vertex. You delete this vertex and now you're disconnecting the graph. Right. So the advantage of this viewpoint is you don't have to worry about the number of vertices, the number of components you get once you delete the vertex V. Some of you made drawings where you get 3 components, 5 components. You have an argument that works. The point is that you don't actually have to worry at all. Once you have this picture in mind, the argument is very straightforward. Right? Less notation, less work, finishes fast. Yeah. Right, so now consider this and see if you can finish the proof in this case. So observe that we can assume our graph is regular, because for irregular graphs you're already done. Right? You can assume the graph is regular. Can G1 and G2 both be regular?
No.
Right? In fact, can either of them be regular?
No.
Right? Neither of them can be regular. You all see that? If G is regular, then neither G1 nor G2 is regular. And if neither G1 nor G2 is regular, then it follows from our earlier discussion that each of them need how many colors?
Delta.
G1 needs delta colors, G2 needs delta colors. Okay, how do you put this together? By making sure that the vertex V is the same color in both colorings. That is okay, right? By just permuting the colors, I can make sure that V is red in both the coloring of G1 and the coloring of G2. Yeah? So now take the union of the two colorings and you have a coloring of G using delta colors. Because delta of Gi is less than or equal to delta of G. Right? Yeah. All done? So we are done with graphs that are not too connected. Yeah? So now we are left with two connected regular graphs. We will drop regular. We will now prove Brooks theorem for all two connected graphs. Yeah, the only purpose of regular was to get rid of not too connected. Very strange. But well, sometimes very strange. Yeah? So now we can assume our graph is too connected. Is that okay? Okay. So, are there any questions or concerns at this point? Is everybody happy that we can assume graph is too connected? Alright, so then I'll get rid of a few things here. Oh, by the way, this if and only if is a DIY. It is pretty straightforward. So let's record what we have done. G is not regular. Done. G is not too connected. Done. We will actually forget this. I'll put it in brackets. I don't know. We will just use this fact. Henceforth, G is too connected. Yeah? Odd cycles and complete graphs are too connected. So we need to deal with the too connected case. Okay. Let's go back to our spanning tree again. Right? As I said, everything is spanning tree. Now I like to draw it like a tree because it has some advantages. That should be good enough. Okay. So think of this as the root. Yeah, this is the root. And this will be the last vertex in our ordering. Right? So we'll construct an ordering by deleting leaves. So, what would be nice when I reach this vertex? When I reach this vertex, two of the neighbors of this fellow have reused the same color. If that we can guarantee, which of course we cannot guarantee in general, right? Odd cycles and complete graphs, then it would be nice. Then we could just use one of the delta colors for this vertex and be done. Yeah? So it would be great if we could make sure that two of the neighbors of the root have the same color. For example, supposing my tree looks like this. This is the root, and whatever. Supposing my tree looks like this. I haven't told you what I mean by this. Okay. But supposing this is the tree. Then am I done? Supposing this is the tree. Am I done? What does it even mean? What do I mean? I don't know.
Yeah.
We are done? Why are we done?
It's like one of the leaves and the
This one and this one.
Give them the same.
Give them the same color. Why can I give them the same color? What if I cannot give them the same color? Why should I be able to give them the same color? You need something more, right? So what your point is, focus on these two. You are saying that these two are somehow special. Yeah, that's right. But why should I be able to give them the same color?
They are not neighbors to establish.
If they are not neighbors. If they are not neighbors, then I can potentially choose them as my first leaf. This one will be my V1, this one will be my V2. And then I will delete leaves from the rest as I like. But because these are V1 and V2, and because they are not adjacent in the graph G, I can give them the same color. Then I don't have to worry about the rest. They can do whatever they like. And then when I reach here, two of the neighbors are using the same color, I will be happy. So if I could have a tree with this that looks like this, and this is not an edge in the graph G. This dashed line indicates that it is not an edge in the graph G. Then we would be done. Yeah? Of course, I have not stated things formally. So, but you see the point. There are two neighbors of this root, they are actually leaves in the tree, U and B. They are not adjacent in G. That's it. If such a tree exists, then I'm done. When would such a tree exist? When would such a spanning tree exist in the graph? So let's think about it again. What are the properties of the spanning tree? So this is now a rooted spanning tree. Okay, so we have chosen an arbitrary vertex as a root. I will call this a Lovász spanning tree because the proof is by Lovász. One of the nice things about Brooks theorem is that it has many proofs. I'm just presenting the one that is my favorite, and I don't remember any others. But they're all basically spanning tree business. So, what is a Lovász spanning tree? T. It has a root R. There is a root R. It's a rooted spanning tree. R has neighbors V1 and V2 that are leaves of T. These are leaves of the tree, and V1 and V2 are not adjacent in G. Okay, these are the properties. I have a special vertex, the root. That fellow has two neighbors in the tree. These are neighbors in T, not in G. There are two graphs here, so I should specify. The root R has two neighbors in the tree, V1 and V2. They happen to be leaves of the tree. And in the graph G, they happen to be non-adjacent. Yeah? Do you all agree that if we have a Lovász spanning tree for the graph we have, then we will be able to finish coloring using delta colors? Yeah? Convince yourself quickly by a few examples that complete graphs do not have such a spanning tree, and odd cycles do not have such a spanning tree. Nor do even cycles, I believe. I think even cycles also don't have such a spanning tree. Please check. But even cycles, I think, is delta colored. So that's okay. Yeah? Have you convinced yourself? Complete graphs do not have such a spanning tree, and cycles also don't have such a spanning tree. Okay? Yeah? Is everybody convinced that if we have a Lovász spanning tree, then we are done? And that complete graphs and cycles do not have a Lovász spanning tree? Yeah? Is that correct? No counter examples? Sorry, except K3. No, but you won't have the last condition, right? Non-adjacent. You need them to be non-adjacent, so complete graphs won't work. Yeah. Okay? Cool? Yeah? Alright. So now the question is, when does a Lovász spanning tree exist? I don't somehow like this, I don't know. I want something that is not so complicated. This seems a bit too complicated. A spanning tree with all these properties. Is there something simpler? When does a Lovász spanning tree exist? Yeah, okay, think about it. If you have some answers, just write it down and I'll comment on it. So what I want to do is I want to throw away the tree. I don't want a tree to be here. Yeah?
Graph is reconnected.
You're right. 3 connected graphs are actually done. Yeah, that's a good point. So actually you can show that if the graph is 3 connected, then again the proof is actually finished. Which actually also shows how odd cycles are really important. Yeah. But okay, what I want is, I want an equivalent condition where there is no tree. Okay, an equivalent condition without tree. You have to focus on V1 and V2. A graph has a Lovász spanning tree if and only if it has something else. Not easy. Not enough. For example, this is true for cycles. This is true for cycles. If I take a long enough cycle, the statement is true. But cycles don't have a Lovász spanning tree. Yeah, also pay attention to this. Yeah, the second point is very important. I'll write maybe part of it for you. A connected graph, because anyways it has to be connected, has a Lovász spanning tree if and only if G has vertices V1 and V2
something outside, this one connected by something. So you can just put this into this packet and just take it out.
You take a 10 cycle, take 2 vertices and distance fixed. That means that they are degree 1 vertices. Then you will say this is
So I can just connect it using that spanning tree. So I'm not saying that three times.
Okay, anybody else?
This is the
Where's it from?
You want me to you and me and you.
Okay. Anyone else? So when does a connected graph have such a spanning tree? There are two vertices, V1 and V2. We want them to be non-adjacent. Is that right? We want them to be non-adjacent. Do we want anything else?
Have a common neighbor.
We want them to have a common neighbor. Yeah? We want them to have a common neighbor. We want them to be non-adjacent. That means the distance between them is 2. Can I just write that? Distance between them, distance between V1 and V2 in the graph G is 2. Do we need anything else? We need one more thing. This is not enough. Observe that this is true for any cycle except length 3. Any cycle on length 4 or more has vertices V1 and V2. Distance between them is 2. So that's not enough, right? Right? We want something else. There is something else that is coming from this picture here, from the properties of Lovász spanning tree.
Take any other vertex in the path from R to that vertex is not via.
Simplify.
G minus V.
Simplify.
Common neighbor has to have degree.
Sorry?
Common neighbor has to have degree at least 3.
Common neighbor has to have degree at least 3. Is that enough?
We can say that any path from V1 to V2 is not disjoint with this.
Simplify.
Connected.
Something is connected.
What?
Some graph is connected. That's
We
the
delete
same.
V1 and V2.
Delete V1 and V2, the graph is connected.
Yeah.
G minus V1 minus V2 is connected. Observe that
Yeah.
this
Because this is the root, it has to be connected.
is a spanning tree of G minus V1 minus V2. And the spanning tree exists if and only if a graph is connected. Yeah? And G minus V1 minus V2 is connected. Yeah? Okay? These are the properties. Let's make a drawing of this. I have this situation. There are two vertices, V1 and V2. They are at distance 2. They are not adjacent because they are at distance 2. They have this common neighbor. And when I delete V1 and V2, my graph is connected. I'll call this Brooks cherry. Is that okay? Looks like a cherry. Brooks cherry. So the statement is a graph is a Lovász spanning tree. A connected graph is a Lovász spanning tree if and only if it has a Brooks cherry. Is that okay? Definition: he has a Brooks cherry. Yeah? So now we'll try to figure out using Brooks cherry, Brooks theorem's proof. Yeah? Okay. There was a point about 3 connected graphs. Yeah? You're saying that we are done with 3 connected graphs. Why is that the case?
If you remove V1, V2, it's still connected.
That is true.
And you can always find, as long as it's not a complete graph,
Right.
it exists.
So long as your graph, take a 3 connected graph. So 3 connected means it's connected. Delete any vertex is connected. Delete 2 vertices, that's also connected. Okay? That's 3 connected. The point is that if it's not complete, then there will be 2 vertices that are not adjacent. And now you can actually prove that there are 2 vertices that are at distance 2. Just take a shortest path and take 2 vertices that are not next to each other. Okay? So there are 2 vertices that are distance 2. Because the distance is 2, they are not connected by an edge, so it has all the properties you want. Because the graph is 3 connected, you delete these 2 vertices, the remaining graph is connected. So therefore we are also done with 3 connected graphs. Although I am not going to use that.
But yeah, I just wanted to mention it since you observed that we are done for 3 connected graphs. Okay. We will still work with 2 connected graphs and finish the proof. Yeah. Okay. Let's erase some things. Okay. So now I don't need spanning tree and all. Now I can just work with Brooks cherry and forget spanning trees. Let's consider any vertex of, observe that this fellow has degree at least 2, but in fact when I delete these 2 the graph is connected. That means unless there are no more vertices, this fellow will have degree at least 3. Unless the whole graph is just this fellow will have degree at least 3. Yeah? Okay. That's the motivation. Let's consider a vertex of degree at least 3. Is it okay? Yeah? If everybody has degree 1 or 2, then the graph is a path or a cycle. There's nothing to be done. Yeah? So let's consider, let V be a vertex of degree at least 3. Yeah? Let's make a drawing. V is this vertex, and some vertices here might be neighbors of V. This is my N of V, vertices that are neighbors of V, adjacent to V, and these are the remaining vertices. Right? So this is going to be a slight generalization of your 3 connected point. Supposing G minus V, if G minus V is 2 connected, let's consider this case. Let's suppose that the graph after deleting this vertex is 2 connected, which is always true if your original graph is 3 connected. You delete one vertex, it is 2 connected. So that's why it is a slightly more general. Let's consider that after I delete this vertex, the graph is 2 connected. Then I claim that we are almost always done. If this graph is 2 connected, then I would like to claim that we are almost always done, whatever that means. Let me make some, so that maybe I'll draw this outside, enough views. These are the neighbors of the vertex V. I would like to say that if G minus V is 2 connected, then we are almost always done. What do I mean by that? Can you see a small condition which would tell us that we are done?
G is not connected to every
Sorry?
vertex. G is not V is not connected.
V is not connected to every vertex. There is a fellow here. If there is a fellow here, then we are done. Yeah? If this set is non-empty, if this set is not equal to the empty set, then what it means is that there is some vertex here who has a neighbor here, right? Because the whole graph is connected, so therefore take any edge going from this side to this side, right? So there will be some vertex here that has a neighbor here. Call this W. I claim that there is a Brooks cherry. Do you see a Brooks cherry? What are the leaves of the cherry? The leaves of the cherry are V and W. Right? Because remember what we assumed? We assumed that G minus V is 2 connected. That means G minus V minus W is connected. If G minus V is 2 connected, G minus V minus W is connected, that is this condition, and V and W are at distance 2, because this is not in the neighborhood. We assume that this is empty. So if G minus V is 2 connected and there is a vertex here, which means that the V is not joined to everybody. A vertex that is joined to everybody is called a universal vertex. Okay? So V is not universal and V is not universal. That's basically this condition. Then we are done. Okay? So we took a vertex of degree 3 or more. Yeah? And we assume that this graph is 2 connected and this vertex is not universal, then we are done. We made a bunch of assumptions in life. Yeah, okay.
If V is universal, it's connected to everybody, we can use that like regular fact, then it has to be a complete graph.
Maybe. So there are many ways to finish the proof, right? Yeah, so you can actually, there are like a lot of pathways to finish the proof here, right? So I'm going to go somewhat in that direction, right? So now let's suppose that this assumptions we made do not hold. What does it mean? We took a vertex of degree at least 3 that is not universal. Is that universal okay? Universal means joined to everybody else. Universal means that the degree of the vertex is actually delta minus 1 because we are dealing with simple graphs. Not delta, n minus 1. Yeah, universal vertex is a vertex whose degree is n minus 1. It's joined to everybody else. Yeah. So, if there is a vertex of degree at least 3 that is not universal and this graph is 2 connected, then we are done. So that brings a question. What are those two connected graphs where every vertex of degree 3 or more is universal? Yeah? Can we write that down? What are those two connected graphs? What are the two connected graphs in which every vertex of degree 3 or more is universal? If I can tell you that these graphs are all these graphs, then we can just check Brooks theorem there and finish it. Is that okay? In which every vertex of degree 3 or more, degree at least 3, is universal. Let's look at this question for a moment. Yeah, we are trying to answer another question here. It's like a small aside. What are those two connected graphs where every vertex of degree 3 or more is universal? Yeah? Is the question clear? So can you tell me some example? Can you think of a class of graphs where every vertex of degree 3 or more is universal? Complete graphs.
Star graph is something.
Can you check again? Can you draw the star graph and check? Two connected.
I mean, like 2 star graphs are universal.
All the cycles.
Cycles. Do you all agree? Complete graphs of this property. Every vertex of degree 3 or more is universal. Cycles of this property, because there are no vertices of degree 3 or more. Yeah, trivially. Yeah, you all agree?
Yeah.
Something like the union of 2
Okay.
stars.
Any other classes? See if you can draw any other graph with this property. Right, so I want a graph
Oh yeah.
that is neither a cycle,
Like something like K2, or something.
draw it, neither a cycle nor complete. See if you can all draw such graphs. Every vertex of degree 3 or more should be universal. Yeah? Yeah, draw it. No, two connected. Yeah, two connected graphs. See if you can draw such graphs. It's a fun little exercise.
This can be an Olympiad question. Maybe it's fancy. No, I'm not sure. Maybe one of the preliminary test questions. I've never really contributed or participated. I don't know what I'm talking about. Yeah. What is it? Generalize.
Sir, I can.
Now see if you can make anything else. If you've already made something, make more. Until you can't make any more. And if you can't make any more, then prove that these are the only ones. Yeah. Generalize. Draw a graph in this class. Okay, anybody else? Did you find any graphs like this? Yeah, try. Every vertex of degree 3 or more is universal, is that right? Yeah, that's what I wrote. So I'll give you a hint. Partition your vertex set into two sets. Vertices of degree 3 or more and vertices of degree exactly 2, because it's 2 connected, right? So degree 1 is not interesting, right? So either you have a vertex of degree exactly 2 or the vertex has degree 3 or more. Now you try to see if you can figure out what are all these graphs.
So each case, this is all the graphs.
Okay, anybody else? So complete graphs are there, cycles are there, right? Anything else? Observe that this graph also has a property. Now can you generalize this graph into a family?
K2, N.
Extra. K(n)(1)
Plus extra edge. Yeah. So it's basically, you can generalize like this, right? This also has a property. Observe that the vertices of degree 3 or more are only these two vertices and they are joined to everybody. So here is an exercise. Prove that all these graphs are either complete
or cycles or k2 comma n plus one edge joining these two. That's it. Where n is at least, I don't know, 1 works. Not two connected. That's what's wrong. Yeah. Yeah. Yes. That's it. Yeah. Cool. Right? So this is an exercise. In case you haven't figured it out, that's okay. It's not too difficult. It's a DIY. Let's look at these graphs. So we know all these graphs once you solve this DIY. Okay? So if you know all these graphs, well, you just go and check whether there's a Brooks cherry or not. Do you all see a Brooks cherry? Yeah? Do you see a Brooks cherry?
Yeah.
Yeah? If everybody sees one, then there is a Brooks cherry. Is that right? Is that how it works? Okay, fine. Yeah.
If G minus V is 2 correct, is the condition.
Yeah, we'll come to that. So, we are going back. We are not done with the proof. Okay? So, what we did is, we took a short aside and we answered this question. What are the two connected graphs in which every vertex of degree at least 3 is universal? Okay? So, because we know all these graphs and they all except these ones have a Brooks cherry, we are done. Right? So, all we have to show is the existence of a Brooks cherry. Right? So, now let us assume that our graph does not have this property. So, it's a two connected graph in which there is some vertex of degree 3 or more that is not universal. Yeah, okay, so let's write down again. G has some vertex of degree at least 3 that is not universal. Now this figure is not lined. This is actually non-empty. This is not equal to empty set. I am choosing a vertex V of degree at least 3 that is not universal. Is that okay? Because if every vertex of degree at least 3 is universal, then the graph has to be this, this or this, and these have a Brooks cherry, so we are done. Yeah? Okay. So now we are going to assume that there is a vertex of degree at least 3 that is not universal. That is this vertex V. Now, G minus V may be 2 connected, may not be 2 connected. If it is 2 connected, then we are done. If G minus V is 2 connected, done. Right? Because we took some vertex like this, W, and now this is a Brooks cherry. Yeah? So, we are now going to consider the only case that remains, which is that G minus V is not 2 connected. Now suppose that G minus V is not 2 connected. This is the case that remains. The only thing that remains is there is a vertex of degree at least 3 that is not universal, and for such a vertex that we chose, the graph G minus V is not 2 connected. Yeah? This is the only case where we now need to show that a Brooks cherry exists. If we show that, we are done. Everybody with me? Questions, concerns? So why this proof and not something else? Why did I choose to present this and not something else? Any guesses? I could have chosen to present many things. Why this theory?
Because it's fun.
It is fun for sure, but there are many things that are fun. Think about all the things you have used so far.
We almost always use
You want to
two
prove
kinds.
that G minus V, if it's like not
The
to
not to
connected, G is
connected.
also not to connected.
Not sure, but anyways, why did I choose this? What is the point?
Because it links to the fact that G is 2 connected and 3 connected, like we talked about it earlier.
Okay, so you mentioned connectivity. Have you used any really non-trivial facts so far? Of course, once you see things, it automatically become trivial. So non-trivial, trivial is very complicated, right? I mean, what is trivial, what's not? The point is that connectivity plays an important role. Even facts like a graph is a spanning tree, it's very easy to just ignore it. Connected graph is a spanning tree or whatever. But we used it. Right? It's useful. It's very useful. Right? And even this Brooks cherry, what is it? It is the existence of a special type of spanning tree. It's all basically boiling down to connectivity. At some very fundamental level, Brooks theorem largely boils down to having a deeper understanding of connectivity. If there is any topic in graph theory that you would like to master, it's not matchings, it's not colorings, it's connectivity. Right? Any kind of graph theory you do, whether it is matchings, colorings, whatever, algorithmic, extremal, probabilistic, I don't care, connectivity is fundamental. Right? And by connectivity, I don't mean just whether a graph is connected or not. I mean these higher notions of connectivity, 2 connectivity, 3 connectivity, K connectivity, and there is also edge connectivity, which we haven't talked about much, but you can look at that. Right? So there is 2 notions of connectivity, vertex and edge, and what we are mostly discussing is vertex connectivity. Deleting a vertex keeps it connected, but there is also a notion of edge connectivity. Right? So if there is one topic of graph theory that you would like to master, it's connectivity. Right? So that's one of the reasons I really like Brooks theorem proof, because it really shows how fundamental connectivity is. And that is actually where we are stuck now. We have a graph that is not too connected. So what? We need some theory. What do you do with a graph that is not too connected? Okay, it's connected,
Or vertex deletion.
but it's not too connected.
There's a vertex which you can delete to ensure that.
True, but that won't actually help us. We will need more theory. Okay, so to finish the proof from here, we are going to need a little bit more theory. We are going to have to understand what do connected graphs that are not too connected, what do they look like? Okay, some of you may have already seen some of these things, I'm not sure, but there is a very nice decomposition of connected graphs that are not too connected. Okay, let's try to make some example and we will finish the proof there. Okay, so let me get rid of this. See if you can all make a large connected graph that is not too connected. So not too connected means that there is a cut vertex. You delete the vertex, the resulting graph is disconnected. Try to make an example with not just one cut vertex, but with many cut vertices. Right? If you need 20 vertices, use 20 vertices. Right? Make a graph that is connected but not too connected and has several cut vertices. Let's say at least 5 cut vertices. Just make such a graph. Okay? Yeah, draw a graph on 20 vertices. Connected but not too connected and has at least 5 cut vertices. Just draw it. Make it more interesting. Don't give me a path. Don't give me a long path. Yeah, this is more interesting. Make it more interesting. Yeah, that was interesting. How many cut vertices? Okay, make it fun. 20 vertices, 5 cut vertices. cut vertices.
2, 3, make it 5.
You see your face in the mirror and start doing it.
Very nice example, but it's too connected. This one, how many cut vertices? Good. That's good. Okay. Yeah.
Wait, so you want the graph to be not connected, but connected? But not connected. By you just do a line.
It's the past. But this one.
This one is too connected.
This is too connected.
This one is too connected.
This side.
Okay. So now I'll make one. Yeah.
I'll put it. I'll improve the graph and it's
A good time.
He drew it self-portrait. After the new thing. He drew self-portrait.
Graph is not too connected.
Like,
No, it should be disconnected. There should be lots of vertices such that if I delete any of them, the graph is connected.
I is connected but not too connected.
There are too many.
Just like do my graph and then replicate here.
So I'll make one example. Now that you all have made some examples. Is that okay? Is that a connected graph that is not too connected? Yeah? Okay. Let me make it more interesting. Okay? Fine? Okay, that's my connected graph that is not too connected. Okay. What we'll do is, when you have a graph that is disconnected, you look at its components. Is that correct? That's a standard thing to do in life. In a similar way, there is another thing you can do here, a standard thing. We will look at because the graph itself is not too connected, we will consider maximal two connected subgraphs. Okay? Maximal two connected subgraphs. There is one problem. Basically what should happen is every edge will go into one such fellow. This needs a proof. Okay, there is some very basic theory that I am going to present without proving. But observe that this edge, it can't be part of any two connected subgraph because K2 is not two connected. K2 is a problem. What we will do is, we will call these bi-connected subgraphs, where bi-connected means either two connected or K2. Okay?
I have a better way to deal with this in my course, but here I'm not doing a full treatment of graph theory as much as I do in my course. Right? So we are going to look at maximal bi-connected subgraphs. Okay? And think of it as a partition of the edge set. It will be a partition of the edge set that needs a proof, which we won't prove. I just want you to do it for this example. Draw this example or whichever example you have drawn already and see if you can figure out the maximal bi-connected subgraphs. Let's do one example here. What about this? Is this yellow colored edges and the corresponding vertices? Is it a maximal bi-connected subgraph? Maximal? No. Why?
Because that edge.
This edge I can include. Now is it a maximal bi-connected subgraph?
Yes.
Now it is. Can you do it for your example? Your example with at least 20 vertices and 5 cut vertices.
It's a subset of the edges, right?
We will just color the maximal bi-connected subgraphs. Think of it as a subset of the edges.
Okay.
Yeah, think of each such subgraph as a subset of the edges and you take the vertices that are included in those edges. Right? For example, in this case, I have 1, 2, 3, 4, 5 edges and I will consider these 4 vertices as included and the others as not included. Yeah? Okay. Just do this for your example. While you do it, I'll do it for my example here. Okay. Is that okay? Did I make any mistakes? I mean, I did at some point, then I corrected it. Now is it okay? Do you all agree that these are the maximal bi-connected subgraphs of this graph? They happen to form a partition of the edge set. Every edge has received exactly one color. Well, I don't have enough colors, but you get the point. Right? This pink color is supposed to be different from this pink color. Anyways. Okay? But anyways. So, you can think of this as a partition of the edge set. This needs a proof. I'm not proving it. What we will now do is, we will now construct a tree from this. Okay, we are going to construct another graph from this to just look at some concepts which we will find useful to finish the proof there. Okay, so what we will do is we will construct another graph from this. This new graph is going to have two types of vertices. These maximal bi-connected subgraphs, there is a shorter word for it so that I don't have to say this long thing every time. They are called blocks. These are called blocks of a graph, blocks of a connected graph. What we'll do is we will, for each block, we will put one vertex in the new graph. Okay? So if B1 is a block, then I will have a vertex B1 in the new graph. Okay?
Yeah, that's good.
So I will have one vertex for each block, B1, B2 and so on. And there are cut vertices. What are the cut vertices? They are the vertices where two or more blocks collide or meet. This is a cut vertex. This is a cut vertex. This is a cut vertex. You get the point? Yeah? So what we'll do is we'll put the blocks on one side. We'll put one vertex for each block. And we'll put one vertex for each cut vertex. Little c1, little c2, little c3 and so on. Okay? Can you all do that?
Yeah.
And now we'll put edges between them in the most natural way you would imagine. A cut vertex and a block
will be adjacent in my new graph if that cut vertex is a part of that block. Right? For example, if I look at this block, little c1 will be adjacent to the block b1, little c2 will be adjacent to the block b1. Yeah? But little c3 will not be adjacent to b1. You all agree? This is a bipartite graph, also known as two-colorable. Right? All edges go from the blocks to the cut vertices. Observe that this graph is not only bipartite, it is actually a tree. There are no cycles in this graph. This needs a proof again. Okay? The reason this is true is because we took maximal biconnected subgraphs. If there was a cycle in this graph, you would be able to get a contradiction to the maximal biconnected subgraph condition. Okay? So, this is called the block tree of a connected graph. If your graph is too connected, then it is completely uninteresting because it will just be a single vertex, K1. But if your graph is connected but not too connected, then it is more interesting. Okay? Fine? So, do you all agree that for this example you will get a tree? Can you just draw it? Can you draw the block tree and see that it is actually a tree? Yeah, do you see it? Is the block tree a tree? Okay. A tree has at least two leaves. Yeah, it will come to haunt us again. A tree has at least two leaves. Therefore, in the block tree, can the leaves be cut vertices? The leaves cannot be cut vertices, right? A cut vertex has to be part of at least two blocks. Do you see that in this example? Yeah? The leaves are going to be on the left hand side. The leaves of this tree, those blocks are called the end blocks of the original graph. So can we look at the end blocks? How many end blocks does it have? Can you all count? How many end blocks will you get? Is B1 an end block? B1 is not an end block. What about this fellow, B2? B2 is an end block? You all agree?
Yes.
Okay. What about this fellow, B3? Not an end block. You all agree? What about B4?
Yes.
Just this one edge.
Yes.
End block?
Yes.
Okay. How many end blocks? Count. You don't really need to draw the block tree. You can just draw it, count it directly in the original graph. Right?
7.
How many end blocks? 7. Okay. Can everybody else verify?
Yes.
Is 7 the universal correct answer?
Yes.
Yeah. Yeah. Everybody says 7.
Yes,
Yes.
yes.
Yeah. Okay. Right. 1, 2, 3, 4, 5, 6, 7. Yeah. 7 end blocks. Okay. All right. So. And an end block, how many cut vertices does it have?
1.
Of the cut vertices of the original graph? 1. Because it's a leaf, right? Okay. But do you also agree that a block has at least 2 vertices? The only exception to that is when your whole graph is K1. If your whole graph is K1, then the block is K1. Okay, fine. But otherwise, a block has at least 2 vertices. Okay? So the vertex that is not a cut vertex is called a internal vertex. In this block, this is an internal vertex. Yeah? In this block, how many internal vertices? 3. These are the internal vertices. Okay? Now we will use all of this theory that we did not prove to smash that problem. Is that okay? So let's see where we were. We took a vertex of degree at least 3 that is not universal. Now there are 2 cases. Either G minus V is 2 connected, in which case we are done because we got the cherry. Otherwise G minus V is not 2 connected. Let's make a drawing of G minus V. I will make it a more abstract drawing. Let's see, where do I have some space? Okay, I think this is good enough. So, I am going to make a drawing of G minus V. These are my blocks. Something like this. Maybe more complicated, I don't know. Okay, this is good enough. Okay. Okay, this is something. Okay, so think of this as your more concrete thing here. V has been deleted. I want to put V back in the picture. Okay, we need to locate a Brooks cherry here. We need to locate a Brooks cherry. Okay. The original graph is two connected. Do you agree? The original graph is two connected. I claim that because the original graph is two connected, if I take any end block B, this fellow must have a neighbor here that is not a cut vertex, that is an internal vertex. There must be an edge like this. If there is no edge like this from V, then this vertex will be a cut vertex in the graph G itself. Yeah, you all agree? For every end block of G minus V, there is an internal vertex of that end block that is a neighbor of V in the original graph G. Otherwise, G itself is not two connected. You all agree?
Yes.
Does that seem believable?
Yeah.
Okay, fine. So, this end block there will be a neighbor. This end block there will be a neighbor. Can you now locate a Brooks cherry?
Yes.
Can you all locate a Brooks cherry? Okay, what's your Brooks cherry?
We just take those two vertices.
This vertex U,
And that
this vertex W.
And they cannot be connected because they are both interior vertices.
They are both interior vertices of distinct end blocks because a tree has at least two leaves. So there are at least two end blocks, and in each of these end blocks we took one internal vertex that is a neighbor of V. Okay, so they are also not, there is no edge joining them, that is also clear. Yeah,
So now,
okay.
So now G minus U minus V minus W is connected.
Now G minus U minus V minus W is connected. G minus, I will do first delete V, delete U, delete W, this is connected. Is that correct?
Yes.
This is because, why is this true?
So
These are internal vertices of a block, right? I'm not deleting a cut vertex. This is an internal vertex of a block. Block is maximal biconnected. Whether it is K2 or 2 connected, I delete a vertex, the graph is still connected. And the cut vertex is still there, which joins it to the rest of the graph. Okay? So because we chose internal vertices, this fellow is connected and this fellow is also connected. Yeah? Okay? Okay? Now,
and V has to have an edge into this because it has degree at least.
V has degree 3 or more. V has degree 3 or more. Therefore, V must have a neighbor that is neither U nor W.
Yes.
Therefore, if I put V back into the picture, it has a neighbor that is neither U nor W. Therefore, it is connected to this graph. Therefore, G minus U minus W is connected. This is the point where we use that the degree of V is at least 3. Yeah? So we got a Brooks cherry. This is a Brooks cherry. And if there's a Brooks cherry, then there's a Lovász spanning tree, and then you're done. Right? Yeah? So, are we done?
Yes.
Yeah?
Yeah.
Okay, QAD. Thank you. Yeah, so we did not go into this theory. I skipped a bunch of theory here. This takes a couple of lectures in my course, but it's not actually that difficult. And if you're interested, you can just go check it out or try proving most of the things on your own. It's simply a matter of getting familiar with the definitions, and then most things just follow quite easily. Right? Okay, so that's all as far as the lectures are concerned. But if you want to discuss any other things in the next 5-10 minutes, I'm happy to discuss. If there are any general questions, we can take them. I don't know. Any questions specific to the content before we go to other general things? Yeah?
Can we, for a general two-connected graph, can we do something like this? Similar with Max, taken that upward.
Ah, good. So the question is, This what we discussed here. So let me answer this as follows. So there is a lot of theory related to connectivity. What we discussed is sort of part of the theory of two connected graphs. So for the theory of two connected graphs, so let me put it this way. For most problems in graph theory, you can restrict yourself to connected graphs. If you prove the theorem for connected graphs, you can prove the result or some natural generalization for all graphs, right? So it's very natural to go to connected graphs. But things actually don't stop here. Things continue in the same fashion for a while. In the same sense, for a lot of problems, it actually makes sense to just solve them for two connected graphs, and then using the block decomposition theory, you can extend the result to all connected graphs, and then you can extend the result to all graphs, right? Okay, but it doesn't stop here also. For certain results, one nice example is a famous theorem called Krutowski's theorem, which says that a graph is not planar if and only if it contains either K5 or K33, where I have to tell you what contains means, which I won't right now. Right? If you want to prove Krutowski's theorem, most proofs that I am aware of, they actually deal with three connected graphs. What you do is you develop more theory and you show that if you prove Krutowski's theorem for three connected graphs, then you can actually prove it for all two connected graphs, therefore for all connected graphs, therefore for all graphs. Okay? So there is a theory for three connected graphs, and in the same sense you can break a two connected graph that is not three connected into its three connected pieces, and I cover this in my course. If you're interested, you can go check it out. Yeah, I spend a significant amount of time just on three connected graphs in my course, and then we actually prove Krutowski's theorem using this theory. Yeah. Okay. Any other questions, concerns? No? All good? Yeah? Okay. In that case, we can stop recording, and in case there are any questions that are not to be recorded.